Thinking of how a working fluid is converted into useful mechanical energy and/or electrical energy, you should think of a turbine. It is known as a turbo machine that contains a moving part called a rotor assembly. The device has vast application which includes automobiles, aerospace, electrical generator, gas turbine engine, etc. Which is why, in this video, we'll explore what a turbine is, its applications, parts, diagram, classifications, types, and how it works. We'll also explore its advantages and disadvantages. Let's get started. A quick reminder to subscribe. What is a turbine? A turbine is a rotary mechanical device that extracts energy from a fluid flow and converts it into useful mechanical and electrical energy. This means the work produced by a turbine can be used for generating electrical power when combined with a generator. In the system, there is a set of blades mounted on a rotor that extracts energy from the moving fluid. So, turbines can be more efficient and effective than each other since there are different types out there. Well, the design of a turbine blade has a lot to say about its efficiency. This is why different applications need different designs. In addition, a turbine can also be seen as a device that harnesses the kinetic energy of a fluid such as air, water, steam, and even combustion gases. The energy created is then turned into the rotational motion of the device itself, which is further used for energy generation. The word turbine was introduced in 1822 by a French mining engineer, Claude Bertin. In Greek words, it means vortex or whirling. The credit for the invention of the steam turbine is given to Anglo-Irish engineer Sir Charles Parsons, 1854 to 1931, for creating a reaction turbine. From 1845, 1913 Swedish engineer Gustav de Laval invented the impulse turbine. Nowadays, a steam turbine is designed to use both reaction and impulse in the same unit, typically varying the degree of reaction and impulse from the blade root to its periphery. A quick reminder to subscribe, like and share this video. Applications of turbine. Below are the applications of turbine. Applications of turbines are widely used in electrical power generation. In fact, a large proportion of the world's electrical power is generated by turbogenerators. Turbines are used in gas turbine engines on land, sea, and air. Internal combustion piston engines make use of turbochargers to increase engine efficiency and speed. Turbo expanders are used for refrigeration in industrial processes. The Space Shuttle main engines use turbopumps, a machine that consists of a pump driven by a turbine engine, to feed the propellants, liquid oxygen and liquid hydrogen, into the engine's combustion chamber. Applications of turbines are also common in heat engines because of their high efficiency at high output. Gas turbines are frequently used in heat engines because of their flexibility. One of the specific applications of gas turbines is in jet engines. Wind turbines that operate by transforming kinetic energy in wind into mechanical power are used to generate electricity by spinning a generator. The turbine can be on land or can be offshore wind turbines. Water turbines are used in hydroelectric power plants. They use water as their working fluid. Finally, steam turbines are used in nuclear and thermal power plants. Water is heated to form steam and then flowed through turbines to produce electricity. Note that the primary function of a turbine is for power generation. If you are enjoying the video so far, kindly subscribe, like and share this video. Components diagram of turbine. Because there are different types of turbines out there, their components will vary. For example, a Kaplan turbine makes use of a generator that consists of a starter, rotor, shaft, wicket gate, and blades. A crossflow, which is a modified impulse turbine, has its components as a runner, blades, water flow part, and distributor. Finally, Pelton turbine components include an impeller, runner, nozzle, spear rod, inlet, deflector plate, buckets, and discharge. All these turbine parts will be explained below along with their diagram. Just stick with me. Classifications and types of turbines. Below are the various types of turbines. Impulse turbine reaction, turbine radial flow, turbine tangential or peripheral flow, turbine axial flow, turbine mixed flow turbine. Classifications based on energy exchange between the water and the machine. This is how the fluid flow reacts on the turbine blades, which causes hydro turbines. It can be classified into two, impulse and reaction turbines. Impulse turbines. An impulse turbine is known by its will being driven by the kinetic energy of a fluid that strikes the turbine blades through a nozzle or otherwise. In these types of turbines, a set of rotating machinery is operated by atmospheric pressure. Impulse turbines are suitable for high head and low flow rates. The three types of impulse turbines are Pelton, Turgo, and cross-flow. Although Pelton and Turgo turbines are similar in construction. However, the cross-flow turbine is a modified type of impulse turbine but is just classified as an impulse. This is due to the rotation of the runner at atmospheric pressure. Reaction turbine. Reaction types of turbines operate due to the sum of potential energy and kinetic energy of water. This is due to the pressure and velocity, respectively causing the turbine blades to rotate. The entire turbine is dipped into water in these types of turbines. It changes in water pressure along with the kinetic energy of the water causing power to exchange. Applications of these turbines are usually at lower heads and higher flow rates than impulse turbines. The common types of reaction turbines are Francis, Kaplan, and Dirichlet. Inward radial flow turbine. Water enters the turbine casing through a penstock, travels through the fixed guide vanes to the rotor, and exits from there. Therefore, the inner and outer diameters are as the outlet and the inlet, respectively. Tangential or peripheral flow turbine. In these types of turbines, water flows in a tangential direction to the runner. Pelton turbines fall under this category. 1. Axial flow turbine. The fluid flows parallel to the turbine shaft, turbine axis, in these types of turbines. Kaplan is a type. 2. Mixed flow turbine. In this turbine, the flow enters radially and leaves axially. Modern Francis turbines are known for their feature. Different types of turbines are based on the hydraulic operating range. These water types of turbines are of three categories. 3. Low head turbine. When a hydraulic turbine operating in the head range of fewer than 45 meters is classified as low head. Kaplan turbine is one of these types. If the head is less than 3 meters, it is considered an ultra-low head. 4. Medium head turbine. In this type, the working range for heads of 45 to 250 meters is considered as medium heads. Francis turbines operate in such conditions. 5. High head turbine. These turbines have headed higher than 250 meters. The Pelton turbine is a good example. Classifications and types of turbines based on specific speed. The specific speed of a turbine is denoted by Ns. It is defined as the speed of a turbine with a geometric similarity that generates a unit of power under a head unit. Based on this parameter, water turbines are classified into three classes. Low specific speed turbine. A low specific speed turbine has a value between 1 and 10. Impulse types of turbines operate in this range. For instance, the Pelton turbine usually operates at a specific speed of 4. 1. Medium specific speed turbine. These types of turbines operate in a specific speed range of 10 to 100. The Francis type work at this ratio. 2. High specific speed turbine. The high specific speeds are above 100, which is how the Kaplan turbine works. A quick reminder to subscribe, like and share this video. How does turbine work? The working of a turbine is quite simple and easy to understand, although their working can be different depending on the type of turbine. In this article, I will be explaining gas turbines. In a gas turbine, compressed air is heated and mixed with some fuel. The mixture ignites and undergoes rapid expansion. This expanding air enters into the turbine, causing it to spin. Because of the compressed air, high altitudes do not affect the efficiency of the turbines. This is why they are perfect for airplanes. Advantages and disadvantages of turbine. Advantages: most turbines are easy to maintain. No cavitation. Simple construction. Most of them are designed to work on high head and low discharge. They are easy to assemble. They have high efficiency.